Welcome back. Today we're doing a deep dive into a story of, well, industrial friction. Real grinding day-to-day stuff. It's about a specific, really frustrating operational pain point inside a timber mill.
Yeah, and what's interesting here is how this one recurring failure, something they actually nicknamed the fall in the hole, became their number one headache. It killed stability, profitability, everything. So our mission was pretty clear. Take this really complex, messy operational pain and turn it into a simple, measurable efficiency gain. And the key was doing it by layering intelligent automation onto the gear they already had.
Right, and that cost. The cost of that failure was just immense. This fall in the hole, it sounds kind of funny, but it represented a serious equipment jam.
Oh, yeah. So you've got the lost production time, plus you needed 3, sometimes 4 operators dropping everything to manually intervene, just to clear one jam.
That's huge.
Yeah. We realized pretty quickly that the answer wasn't necessarily bigger, better equipment. It was about smarter sight, giving the existing team the ability to stop the problem before it escalated.
Okay, so let's zoom in. Where exactly was the trouble starting? You mentioned it's a timber mill.
Exactly. Right at the beginning of the process, the infeed, where logs get fed into the main machine center. And the critical piece of equipment there is called the end dogger.
Gotcha. So what was going wrong right there?
Well, the jam itself, the fall in the hole, that was sort of the grand finale of the problem. It always started with smaller things, precursors. Usually it was either a log skewing, meaning it wasn't lined up properly when the dogger tried to grab it, or sometimes even worse, a double log. 2 logs trying to get into the machine at the same time.
Okay. So if the dogger grabs a log that's crooked, or if 2 logs jam up the entrance, disaster.
Precisely. If either of those things happens, the chance of a catastrophic failure, the big jam, it just skyrockets. And the old methods they were using, things like basic photo eyes, they were okay at detecting if a log was there, but they couldn't really judge its shape or how it was sitting, its geometry, its orientation.
They just saw something or nothing.
Pretty much. And they really struggled with the environment in the mill, too. You know, dust, wood chips, moisture, even just the way the light hit things.
Yeah.
It could cause false stops.
Which must have driven the operators crazy.
Oh, yeah. Either false stops, which are annoying, or even worse, they'd fail to detect a real skew. And if that skewed log gets past the point of no return, well, then you're basically guaranteed that 45-minute recovery session.
Okay, you've really painted the picture of the pain point. It wasn't about raw speed. It was about seeing things correctly and acting fast enough. Which brings us straight to the solution, Daemon AI. And what I find really compelling here is what you called the anti-overhaul approach. You weren't pitching some massive multi-million-dollar upgrade, right? What was the actual hardware setup? How lean was it?
It was surprisingly lean, especially by industrial automation standards. We needed one systems integrator partner to help coordinate things on site. Then the core components were just a standard industrial Windows PC, powerful enough to run the AI, but nothing exotic and, crucially, a single IP camera.
Just one camera?
Just one.
Yeah.
It was likely one they already had aimed at that area. The only real requirement was that it supported RTSP.
Okay, RTSP, that's the standard way network cameras stream video, right?
Exactly. Most modern IP cameras support it. So the beauty of it is we're leveraging the investment they'd already made in their camera infrastructure. No need to rip and replace.
That's smart. And the integration time, you mentioned this was up and running fast.
Yeah, remarkably fast. Yeah. The whole system, from installation to actually classifying video and identifying these issues, took just a few days, not weeks or months.
How does the AI learn so quickly? Logs aren't uniform, right? They have knots, different sizes, bark. How did it learn to tell a good flow from a skew or a double log with all that variation?
Right, that's key. The process uses our training application, and it's designed to be quick and intuitive. Mill team basically gave a short video clip showing the end dogger in action. Normal operation, go flow. Then clips of logs skewing, clips of double logs happening. Then in the training app, you just categorize those segments. And then you link that visual category to a specific numeric code that the PLC, the machine's brain, will understand as an alert.
I see. So it's not being programmed with rigid rules like if pixel X is dark and pixel Y is light. It's learning the pattern of what a failure looks like visually.
Exactly. It learns dynamically.
Yeah.
And that makes the AI models really resilient to all the environmental noise, dust, vibration, shadows, changing light, things that constantly tripped up the old photo eyes. Instead of just looking for a simple beam break, the AI is analyzing the whole picture, the geometry of the log relative to the machine, in real time. That makes it far less prone to false alarms or missed detections.
Okay, so the AI is trained, it's watching the video feed. Now the intervention part. What were the two big problems it was trained to spot instantly?
The two main targets were skews and double logs. Those were the precursors to the big jam.
Right. And what happened when it spotted one? What was the specific action?
The action was tailored to the problem. So if it detected a double log situation starting, didn't just slam the brakes on everything. Instead, it sent a specific signal to pause the jack ladder. By pausing that, it prevents the second log from actually entering the end dogger area. It resolves the conflict right at the source before it becomes a jam.
Clever. Okay, and what about if a log was already starting to skew as it entered?
Right. If the model detected a log was already skewing as the dogger tried to engage, then the system instantly triggered a full stop of that production line section. That signal goes straight to the PLC and stops the movement before that minor skew turns into the big, unrecoverable 45-minute disaster.
How does the AI talk to the PLC so quickly and reliably to make sure that stop happens in milliseconds?
Yeah, good question. We achieve that control using really efficient digital messaging. DAI talks directly to the PLC using standard industrial protocols, think Ethernet IP, Modbus TCP, Profinet, etc. We send very small, standardized data packets. They contain the alert code, like skew detected or double log detected, and the AI's confidence level in that detection. And this communication is extremely low latency, and it's also bidirectional. The system can also read data back from the PLC, things like checking if the line is supposed to be in run mode or stop mode. The elegance is really in the efficiency. There's no waiting for some central server to process data in the cloud or anything. It's a direct, immediate command from the edge AI to the machine controller.
That sounds incredibly smooth on paper. But, implementing any new vision system, especially AI, can face hurdles. Did you encounter any maybe skepticism from the operators who are used to the old ways? Or did the mill environment, the lighting, the dust ever cause the AI issues early on?
That's a really fair point. Change is always, a factor. Resistance can happen. We tackled it mainly in two ways. First, during the training phase, we specifically focused on using video from that exact location with its specific lighting, its dust levels, sometimes logs covered in mud. So the AI learned to deal with the actual conditions, not some idealized lab setup. That built confidence quickly. Second, honestly, the operators became the biggest advocates once they saw it working. Instead of dreading that inevitable fall in the hole and knowing they'd be spending a chunk of their shift climbing into machinery or waiting for lockout procedures, now the line just stopped early, when the problem was still small. Usually something they could fix in seconds, maybe a minute, just using the regular console controls, no big emergency. That shift in their daily workflow, that turned any initial skepticism into pretty rapid adoption. They saw the benefit firsthand.
Okay, let's talk hard numbers then. Let's synthesize these wins. Looking at the before and after data, what was the quantifiable impact? How much did these incidents decrease?
So the problem was effectively eliminated, not just reduced, but pretty much gone. The mill's top downtime incident, that infamous fall in the hole, it dropped from happening multiple times every week to fewer than one per month. And it created a continuity of flow, a stability that the facility just hadn't had before. Production became much more predictable. Plus, all that labor that used to be tied up clearing jams, now it could be redirected to, actual productive work.
Makes total sense. How do you stop the AI from being too sensitive? Like, if it sees a tiny shadow flicker for a split second, you don't want it stopping the line constantly, right? Creating nuisance stops.
Great question. That's where something we call the conditioning system comes into play. You can't have the PLC reacting to every single little blip. So we stabilize the output. We require what we call n consecutive identical results above a minimum confidence score before we actually trigger that PLC action.
Okay, so it needs to see the same problem for several frames in a row.
Exactly. For instance, the rule might be, I need to see 3 consecutive video frames classified as skew with more than, say, 60% confidence before I send the stop signal to the PLC. That little bit of delay, that requirement for consistency, it filters out all the momentary flickers or uncertainties. It eliminates those rapid on-off oscillations and ensures the system only acts when it's truly confident there's a real persistent issue developing.
Got it. So it builds in robustness against false positives.
Precisely.
So what does that localized intelligent control mean for the mill's day-to-day operation now? What's the lasting change in how they run things?
It really means more continuous, predictable flow. That's the big one. The AI is constantly watching for all those little anomalies, the skews, the doubles, potential blockages. Interruptions are way down.
This whole case study is fascinating because it really shows that tackling your biggest, most painful, recurring operational problems doesn't always mean you have to shut down the plant for 6 months and spend millions on brand new machinery.
Right.
It demonstrates that sometimes, maybe often, layering intelligence onto the assets you already have, like that existing camera, can deliver really immediate, really measurable ROI.
It absolutely changes the conversation. It shifts it away from just massive capital expenditure towards thinking about smart efficiency gains. And I think the big lesson here, and it applies way beyond timber mills, is that catching the precursor to failure. That's the gold standard. Whether it's a log skewing or a component misaligning at a factory or packaging getting jammed, seeing it early is key. Now, that facility runs much more reliably, much more autonomously in that section. And the operators, their valuable expertise is saved for genuine process tuning and real exceptions, not for dealing with preventable disasters day in and day out.
That's a powerful shift. This is what intelligent automation looks like. To learn more, visit daemonautomation.com.